We will now embark on a very important topic which is called functional approximation. And once we learn the art of functional approximation, we will use it to solve a variety of problems that include numerical interpolation, numerical differentiation, and numerical integration. So, this functional approximation forms the basis of many further topics that we will be discussing in the course. So I strongly encourage you to place a lot of emphasis in learning the concepts related to functional approximation that I'll be covering over a sequence of video lessons. Oftentimes what is given to us is data is given in the form of a table like this. And we will have problems to solve. For example, two such problems are listed in this particular slide. So given this data set, we are asked to find out what is the value of Cp at a certain temperature. Now this table, as you can see, gives many values of temperature and the corresponding Cp values, right? So at 7 different temperatures with a gap of 100 degrees Kelvin, experiments have been done and the Cp values have been noted. So you can see there is at least a remarkable change in Cp over the range of temperature is equal to 100 Kelvin to temperature is equal to 700 Kelvin. We cannot assume it to be a constant value. So one of the things that come before us is what's the value of Cp at 273.16 Kelvin as an example. This particular temperature value is not represented in this table, though we know it is going to be between these two values, and therefore the answer, the Cp value, should be within these two values. But exactly what is the value of Cp at this point? You can solve it by what is called interpolation, for which you will need some equation or what we will call as functions. So what you do is you take this data table and you convert it into a functional form. And we call it functional approximation because nobody knows the true relationship between the temperature and specific heat capacity. So you're going to make some assumptions on the type of relationship and the complexity of the relationship, and you will identify a functional form. In some sense, you will identify a model between Cp and T. And therefore, because we are doing approximation, this topic makes sense to us. This is called functional approximation, right? So we understand that we are going to get functions that are only approximate but good approximations. And once you get an equation or a model or a approximate function based on this data, then you would be able to use it to solve this interpolation problem. That means you want to find out the values of the output variable at some intermediate value of the input variable. Here the input variable is temperature and the output variable is Cp. So you can find out the value of Cp at 273.16 Kelvin using a functional approximation, even though this temperature is not represented in the table, but this value of temperature is within the range of your experimental data. Therefore, we call it interpolation. If we wanted to find out the value of Cp at 900 Kelvin, that would be the extrapolation problem. And you have to proceed with that problem very, very carefully. All right, because our functional approximation is only good over the range of data that was used to construct the equation or function or model. But we will focus on the interpolation problem here. The other kind of problem that you can solve using this kind of an idea is what is called numerical integration. Let's say the question is from thermodynamics, where we are trying to find out the amount of heat that has to be supplied to a gas to heat it from, let's say, temperature T1 is 300 Kelvin to temperature T2, which is 700 Kelvin. And here, since we are given the molar flow rate, we would be computing the heating rate. So if you apply the principle of conservation of energy, or you just invoke some thermodynamics principles, you can get this expression, all right, in appropriate units. So this is in kilomoles per hour. So if you want to convert it into kilomoles per second, 1 hour is 3,600 seconds, and therefore this number should make sense to us. If Cp is constant, we can take this Cp outside if it is constant, and you will have integral of dt from 300 to 700. So if you apply the limits 300 to 700 for t, you're going to get 700 minus 300. So you will get the very well-known form. If Cp was constant, you will get Q is equal to m dot, which is the, let's say, the molar flow rate, and then multiplied by some average CP value times delta T. So this is a form that we have seen in many other courses, right? For example, in our mass and energy balance course, etc. But here we have noted that the CP value is not constant, right? As you can see, as temperature changes, the CP value changes. Therefore, we have to integrate this in this particular way and find out the answer. That means we have to find out a value for Q. So the route is take this data set, convert it into a suitable functional form and exploit that functional form to get the value of this integral. So this leads to numerical integration, which is going to be a very, very important part of what we are going to look at. Now, here is another kind of problem that we can solve. For example, measurements of temperature of an air stream flowing above a surface are measured with a thermocouple. So this is a surface, you can assume, and then there's an air stream that flows over this, right? So there's an air stream that flows here, and you place a thermocouple, let's say somewhere downstream here. Let's say, for example, you place a thermocouple here and you record the temperatures, right? So you kind of record the temperature at, let's say, the surface, at 1 unit distance from the surface, at 2 units distance from the surface, and at 3 units distance from the surface. So you get these kinds of temperature measurements. At the surface, a little above the surface, a little above that, and a little above that. So these are the temperature values that we measure. So again, you can see the data comes to us in the form of a table. Experiments are conducted, sensors are placed at appropriate locations, and some things are measured. But what we are interested in here is to estimate this value Q dot. Again, rate of flow of heat, which is given by this expression minus K times A times dt by dy at the surface. Surface means at y is equal to 0. If you do a course on heat transfer, these kinds of expressions are something what you will see. So in order to compute Q dot, we would have to know the values of thermal conductivity K, the area of heat transfer A, and we also need to know what is dt by dy at y is equal to 0. Now, what our measurements give us is the value of t at y is equal to 0, the value of t at y is equal to 1, etc. But we do not have data on what is dt by dy at y is equal to 0. So from these measurements, you have to be able to get a good estimate of dt by dy at y is equal to 0. This becomes very, very important. This leads to what is called numerical differentiation. We do not have an expression for t as a function of y. That's not given to us. What is given is data on how t changes with y. So what you do is you take this data and you convert it into a approximate function. And we can use that approximate function to find out dt by dy, and you evaluate the dt by dy at y is equal to 0. So we will look at functional forms that will give us specific expressions for things like dt by dy at a particular point. So we would be able to compute the quantities that are of interest to engineers. Typically, the rate of heat transfer in this example as well as in this example, we want to find out physical properties at some values of temperature that are not available in the form of experimentally tabulated data. This becomes very, very important when you're running process simulators like HYSYS and so on, where you will not have the values of physical properties at all values of temperature and pressure, for example, right? So we need to be looking at some experimental data, but we have to rely on functional approximations in order to find out the physical property values at the conditions that the process is operating at. So this functional approximation is a very, very important idea that helps us solve many problems that are of interest to engineers. The overall roadmap is like this. We have tabulated data as I've shown in the examples earlier. We can use those tabulated data to construct functional approximations. And once you have the functional approximation, we can use it for interpolation, we can use it for integration, we can use it for differentiation, etc. All right, so these are the final uses of these functions that we obtain via functional approximation from the data. Now, sometimes what happens is we may also have known functional forms that are given to us. But the known functional forms can be quite complex, that they become unwieldy for fast computations. So when you're doing computations, when you're doing computations after computations after computations, what you look for is good accuracy but low complexity. So this is what is sometimes called as surrogate models. So the known functional form can be highly accurate, but it can be quite complex. So you cannot use it for online optimization, online control, and things like that. There is a necessity for it to be approximated into a form that is easily calculable, but we have to compromise in terms of slightly lower accuracy. So even for those applications, this functional approximation idea can be quite useful. As an example, I can take a very complex nonlinear function and construct a quadratic approximation to it. And I can use the quadratic approximation for my calculations. And once I get a good answer with the approximate model, I can take it back and correct it with the known complex functional form. I can do a lot of exploration using the functional approximations, and once I have explored enough, I can take the most promising candidates and now process it through the high accuracy, high complex functional form. All right. So sometimes even with known functional forms, this functional approximation idea can be quite useful. And we can use the approximate functions to do interpolation, integration, differentiation, etc. Of course, if you have enough computer resources, you can use the known functional form, which can be quite complex. You can use it directly for interpolation, integration, and differentiation. The key word for some of you may be what is called surrogate models. So the known functional form can be quite complex, so you simplify it in the form of surrogate models, which you can solve very easily. So you find an approximate answer with surrogate models, and then take it back to this highly complex model and get more detailed and more accurate simulations done. So with this introduction, I'll stop this video. I'll catch up with you in the next video. Thanks for your time.